Hello dear listeners and viewers. From my last video you know that the Schrödinger equation and quantum mechanics appeared as a result of development of de Broglie's hypothesis that atomic particles exhibit wave properties. Now, before we start working with the Schrödinger equation and wave functions, I will show some simple but very interesting examples of working with de Broglie waves. For the beginning, let's quantize so-called infinite potential well. What is this problem about? Let's imagine the following sketch. I walk into a narrow corridor somewhere or into a small empty room with a ball in my hands, and then I put the ball on the floor and kick it at the top of my strength just perpendicularly at the wall. What will happen? The ball will fly back and forth, bouncing off the walls. Gradually, it will stop due to energy loss due to friction. In the ideal theoretical case, there is no energy loss due to impacts on the walls or friction against the floor and air. The ball flies between the walls at the same speed for an indefinitely long time. This is exactly the formulation of the problem of a particle in a squared potential well with infinitely high walls. Just fine. Now I reduced all dimensions and take a toy ball in the box. You see the same picture. Then we can further reduce all dimensions in thought or real experiments and reach atomic sizes. Here, the behavior of our ball, or more precisely of an atomic particle, changes dramatically. The particle begins to exhibit wave properties. At this point, however, one good question immediately arises. What system does this well describe? The answer is as follows. There are no exactly such atomic systems or processes in nature. There are only closed quantum processes, such as channeling of electrons, protons, and neutrons between crystalline planes and the movement of electrons in thin semiconductor films. Thus, a one-dimensional potential well is rather a purely theoretical object, but it describes in clear and absolutely correct way all main peculiarities of quantum effects observable in real atomic systems such as atoms, molecules, crystals, etc. In fact, the infinite potential well is the best object for an initial introduction to the cooking house of quantum mechanics. All university textbooks on quantum physics examine this topic. We will also do this now, but instead of determining energy levels as so-called eigenvalues of the Schrödinger differential equation and then defining the corresponding eigenwave function for the equation as it is usually done in textbooks, we will find energy levels from quasi-classical quantization rules and then draw the wave functions just intuitively at this stage. Now we will see how this works within the framework of the old quantum theory. First, we will draw a particle between the walls. Next, we recall the expression for the de Broglie wavelength. Finally, we will apply the so-called Bohr-Sommerfeld quantization rules. These rules say that for stationary or long-living states, an integer number n of de Broglie wavelengths lambda must fit within a period of motion of the particle. Note that quantization rules are usually introduced through so-called action integrals, but here we use wavelengths, which is actually the same, but just a bit more simple. Now we will make some transformations. If I multiply the upper equation by n and then substitute 2a instead of lambda n, then we have new equation and continue work with it. In the next step, we multiply both sides of the equation by v over 2a. Next, we need to make some reductions in the numerators and denominators in the left and then in the right side and obtain finally the simple formula for quantization of the velocity. Okay, after that we recall that kinetic energy of the particle is equal to the half of mv squared. The kinetic energy is equal to the total energy, since there are no any external forces between the walls. Then we substitute the upper relation for the speed and make some simplifications. Then we denote the energy level with n and scratch interim calculations. Thus we have got the result. This is the formula for quantizing the total energy levels of a particle in an infinite potential well. I would like to point out here that sometimes you may see a different formula with 8 instead of 2 in the denominator. This means that the origin is chosen at the center of the well. Then a is equal to 2b as in the figure and a squared is equal to 4b squared. Now we'll draw at a qualitative level what the Broglie waves look like for this well. In the simplest case, we have one wave per cycle. Total energy is calculated with n equal 1. We must fit half a wave from wall to wall. Let's draw. It looks like this. The remaining half wave does not go to the right. It reflects off the wall and goes back like this. Finally, we have the following picture. Okay, now we draw when two waves fit on the cycle length 2a. We draw one wave to the right, and the second wave returns to the left. Wonderful. For energy levels, we have E2 is equal to the same factor as above multiplied by 2 squared. Okay, now draw three waves. One wave goes right, the second wave hits the wall and goes back, and then the third wave completes the cycle. For energy 3 we have the same formula but now multiplied by 3 squared. To depict the all energy levels on the graph, we will plot the coordinate along the x-axis and the values of total energy and potential energy will be plotted along the vertical axis. Then the picture of the levels looks like a ladder. We can also show the corresponding de Broglie waves in this picture. Note that our drawing is based on the simplest qualitative use of the Bohr-Sommerfeld quantization rules. The exact shape of the waves and their time evolution is usually determined from the solution of the Schrödinger equation. However, our analysis and the Schrödinger equation give identical results for the energy levels and general structure of the waves in the potential well. Looking ahead, you should also note that the Schrödinger equation says that our waves are so-called standing waves. This means that they oscillate over time, but positions of the crests, troughs, and nodes remain unchanged. We will discuss this time evolution in future stories. I am also obliged to drop a remark here. There are no any trajectories, and we do not see any time movements of the particle within frames of quantum theory based on the Schrödinger equation. Only wave functions are allowed. Mentioning of trajectories is allowed but not encouraged. In this presentation, I assume the existence of trajectories for quantum particle to simplify understanding. Now we will briefly discuss the consequences of quantizing energy levels in the well. We can launch a particle with any total energy into a classical well. It will oscillate there unlimitedly long in time. But we cannot do the same with the quantum well. Within a short time, the system will rebuild itself. The particle will occupy one of the stationary energy levels we just identified. In most cases, this will be the nearest lower level. How exactly this happens is not really clear. We only know that this depends on the experimental conditions of the particle captured by the well. We also know that highly likely a photon or a set of photons will be radiated during this restructuring. Now we have just come close to discussion of another important effect. Let's assume that our particle is an electrically charged particle like an electron. Then it is well known from so-called electromagnetic field theory in physics that charged particles emit photons when moving with acceleration. When hitting the wall of the squared potential well, the acceleration is infinite and the energy emitted is also infinite. Then we slightly change terms and assume that the potential walls are almost vertical but have some minor slope. In such a case, the acceleration is limited and energy emitted in the form of photons is also limited. Our classical particle loses a small amount of energy after each impact on a wall and its movement gradually slows down. As for the quantum particle, it cannot lose a small portion of energy. The particle is oscillating between the walls with the same speed and energy for some relatively long time. Then suddenly it jumps to the lower level, losing energy in the form of one photon. This phenomenon is called as the quantum jump. The moment of the jump is not predefined and changes randomly. Its probability can be calculated on the basis of the Schrödinger theory and Einstein's theory of radiation. There is nowhere to jump from the first level and the particle exists on it for an indefinitely long time. Therefore, the first level is often called the ground state. What exactly leads to quantum jumps is still not known with certainty. Moreover, it is not known what will happen if a particle with an energy lower than the energy at the ground state is placed in the well. It cannot occupy a stationary state because there is not enough energy. But then what will happen to this particle? There is still no exact answer to this question. This is one more example of unresolved secrets of quantum physics.